When the pH is 7, then it's a case where the sample is neither acid nor base. But less than 7, it's an acid, we say. More than 7, it's a base all the way.
Before we start talking about titrations in more detail, I quickly want to go over those concepts of endpoints and the equivalence point. What difference between the endpoint and the equivalence point is. So for example, if you have a strong acid and strong base, they will neutralize each other if we have equal amounts of moles. So for example, if you have 1 mole of a strong acid and 1 mole of a strong base, in many cases, that means we have 1 mole of hydrogen ions and 1 mole of hydroxide ions. And when they come together, the hydrogen and the hydroxide ions, they will form H2O. And that is obviously neutral. So in that case, if we have equal amounts of hydroxide ions and hydrogen ions in solution, they'll come together, and overall we'll be left with only water, and water will have a pH of 7. Let's say we want to find out at what point we have equal amounts of moles of the hydroxide ions and the hydrogen ions in our solution. So what point are these and these equal? Well, we know that it's the case with strong acids and strong bases. So if we have a titrant being our strong base and our aliquot being a strong acid, then that should happen at a pH of 7. So our pH of 7, in the case of strong acids and bases, would be our equivalence point. Because what our equivalence point means is it's the point at which all bases and acids have reacted together. So the point where our hydroxide ions from the acids and our hydrogen ions from the acids and our hydroxide ions from the bases, the point where they've all come together and have reacted to form water. And this point is a pH of 7 for strong acids, strong bases. So equivalence point is that theoretical point where we know that it has happened. Now the end point is to do with indicators. So it's a point where the indicator just changes color. So for example, let's say we use bromothiamyl blue. So let's say we put into our flask, we put bromothiamyl blue. Now it changes color. At its range is quite good because its range will be about from 6 to 7.6. And you can see it will change to a greenish color at 7. So that means if we take bromothiamyl blue as our indicator and it turns green, that means we know, okay, it must have a pH of 7. So that means the endpoint and the equivalence point are almost identical. Right? So the equivalence point is a pH of 7, and our endpoint, so when it changes color to green, is also 7. So that's good. Now endpoint and equivalence point match. But let's say we don't put bromothiamyl blue into our flask for a strong acid and strong base titration. Let's say we put in phenolphthalein. So phenolphthalein. Put that into our flask. Now its range is about from 8.3 to 10. So it's going to change its color from 8.3 to 10. So in this case, let's say the indicator changed color, and that means it'll change color at about a pH of 8.3. Now for us that's relatively useless because that means the endpoint, which in this case for this indicator will be 8.3, and the equivalence point, which is still the same equivalence point as 7, will be quite far apart. So we can't use that indicator to examine the equivalence point of a strong base and strong acid titration. So what we have to do is we have to actually match the correct indicator with the type of titration we're doing. Strong acid, strong base, we usually use bromothiamyl blue because it's the appropriate endpoint. It's quite similar to the equivalence point. We won't be using phenolphthalein because it's going to be quite different. So that's just the overall idea of equivalence point endpoints and why we need to use a suitable indicator to actually do different types of titrations. So the dot point itself says perform a first investigation and solve problems using titration and the preparation of standard solution. That's one part. That's part 1. And use available evidence to quantitatively and qualitatively describe reactions between selected acids and bases. And that's the second part. And this video we're actually only going to cover the second part. We're going to cover the first part in the next video, so the video after this. But for this video, it's just the second part, to quantitatively and qualitatively describe reactions between selected acids and bases. Now these are the 4 possible titrations we can do. We have either a strong acid and a strong base, or a strong acid and a weak base, or a weak acid and a strong base, and a weak acid and a weak base. These are 4 possibilities of our titrations. Let's assume for the first titration we have a strong acid which is, in this case, our strong acid is actually our L-equate. This is our flask. So in our flask is a strong acid. And our strong base, so the concentration we don't know about, is our titrate. This is the unknown concentration. So this is the graph of what it will look like. We have pH on the one side, and we have the volume of added base on the other side. What's going to happen for a strong acid, strong base solution, titration, is you're going to have no real change in pH until basically we've almost reached the equivalence point. So once we get close to the equivalence point of them being completely neutralized, so the acid will produce the hydrogen ions, and the bases will produce the hydroxide ions. So once we have our hydronium and hydroxide ions, which is the same as our hydrogen and hydroxide ions, once they have been completely neutralized, so once they're completely gone, we'll only have water being produced. Because of the strong acid, strong base reaction, we have no reverse reaction, so nothing will be reversed. It's all going to be just going to water. And once that point is reached, once they have mopped each other up, then we have a sudden change in pH. Because any additional base that we add will have a massive effect on the actual pH. So what you can see, it'll change from about 2.5-ish, so pH of 2.5 to about a pH of about 11. It'll be very sudden, that change. And our equivalence point is actually in between those two values. So about 2.5-ish and roughly like 11-ish. Our equivalence point will be in the middle. And that happens to be at around about a pH of 7. So our equivalence point is always in the middle of that steep rise. In this case, in strong acid, strong base reaction, that equivalence point is a pH of 7. Now, what kind of indicator could we use? Well, again, these are the possible indicators. We've got methyl orange, litmus blue, bromophenol blue, and phenolphthalein. And we said earlier, for bromophenol blue, we have a change in the color at around a pH of 7. So it changes from yellow-green to green, and then to green-blue. So we can use bromophenol blue to indicate to show us the equivalence point. So we're going to use, our indicator will be bromophenol blue. Bromophenol blue. Because that will give us the appropriate equivalence point. It's close to equivalence point. So endpoint and equivalence point will be quite close together. Now for a strong acid and weak base reaction, so in this case again our strong acids are in our flask, our L-equate, and our weak base is in our actual titrate, so in our burette. So we start with the same pH because we have a lot of strong acid in there. And what's going to happen is same thing, it's going to stay stable. And then it's going to be a less severe rise. It's still going to be quite sudden, so you can see it's still going to go from about 2.5-ish, but this time it's only going to go up to about 8-ish. So 8-ish. And remember, the equivalence point will be in between those two values, so it'll be roughly at 5-ish, so 5.3 for a strong acid and weak base titration. And the reason why that is, if you don't remember what happens when it comes to neutral, acidic, and basic salts, make sure to watch that video. Because in this case, we've got a strong acid, and that means we actually have some reverse reaction happening. And when that happens, even when all the strong acid and base, even when they have all reacted together, strong acid and base, we'll still have some pH, some hydronium ions in a solution, which means we actually have a lower pH. So overall, even when they're both completely equalized, neutralized, we will still have some hydronium ions left in our solution, which means our pH will be lower. Make sure to watch, I'll actually put up a link here, so you can watch this link if you are a bit confused about neutral, acidic, and basic salts. You need to know that for this video. So yeah, we said 5.3 is our pH. And what kind of indicator could we use to get that equivalence point of 5.3? That's when we have the strong acid and the weak base neutralizing each other. Well, in this case, we can use 5.3. We have a change from orange, red, 4, 5 is orange, 6 is yellow. So in between, again, methyl orange seems to be a pretty good indicator to use to be able to figure out the equivalence point, because it changed color at the equivalence point. So endpoint equivalence point will match if we use methyl orange. So for this, we're going to be using methyl orange as our indicator. For a strong acid, weak base, we use methyl orange as our indicator. Now if we have the opposite, and so now we have a weak acid in our solution, so in our flask, and we have a strong base as our titrant and in our burette, which means we started at a pH which is slightly higher, so it started at a pH of about 2.5 because it's a weak acid. And then we add the strong base, so you can see that rise is more severe because we add strong base to weak acid. Neutralization is happening faster. But you still have a sharp rise. You still have a sharp rise when we have all of the weak acid and the strong base reacting together. Now the sharp rise starts at roughly a pH of, should be about 6-ish, a bit more than 6, and goes up to about a pH of 10, which means you can remember in between is our equivalence point. So equivalence point will be a bit higher than 8. It should actually be about 8.3, I think, for weak acid and strong base titration. Now, what could we use? And again, the reason why that is not neutral, that same video that I mentioned earlier, you need to be able to know that, because if we have a weak acid and strong base, there's going to be still some hydroxide left. Once all of the weak acid and strong base have come together, there's still going to be some hydroxide left in the solution, which means the pH is a bit over 7, a bit higher, because it's a reversible reaction, unlike strong base and strong acid, which is a one-way reaction. So we have a pH of 8.3, and that means we could use the indicator as follows. So 8, we want to have a change at about 8, so that our endpoint and equivalence point match. So if we take the indicator phenolphthalein, that changes from 8 to 9 to 10. That's going to be a pretty one good to use because we can sense the color change with that one. So in that case, oops. So for this one, to make sure endpoint and equivalence point match, we're going to use phenolphthalein as our indicator. Now when it comes to weak acid, weak base titrations, in this case, weak acid would be in here and weak base would be our titrant. We do not usually do these equations, these titrations. The reason why is because if you look at the actual rise, it's going to be gradual. And the problem is when there's a steep rise, in all the other cases there's a steep rise, and we can figure out the actual equivalence point by looking at the middle. But when you have a rise, the same point where you had a rise, like a steep rise in beforehand, you actually have a gradual rise here. So with that gradual rise, it makes it very hard to find out the equivalence point, which is why we don't often do weak acid, weak base titrations, because they can't really be used to get the equivalence point. We want to have a steep rise, we get a steep rise with all the other ones. So if we do have a weak acid, we're going to use a strong base. If we have a weak base, we're going to have a strong acid. We don't do weak acid to weak base titrations. So examples would be, for example, we might have hydrochloric acid as our strong acid, and then we might have sodium hydroxide as our strong base. Those titrations, they will produce salt and water. Strong acid, again, this could be hydrochloric acid. A weak base could be, for example, ammonia. A weak acid could be, for example, ethanoic acid is our weak acid. And our strong base could again be sodium hydroxide. And again, we don't do weak acid, weak base titrations. So these would be just some of the examples. So overall, what you should know, should be that overall we do strong acid and base titrations. We might do strong acid, weak base titrations. And we do weak acid, strong base titrations. What you should know is you should know the equivalence points of each. So about 7 for the strong acid, strong base, because there's a complete neutralization that happened. It's about less than 7, so roughly in the 5 category for strong acids and weak bases. And that's because our acidic salt that is formed when we have a strong acid means our solution will be slightly lower when both have been neutralized. And that means we use a different type indicator. In this case, we use the ethyl orange indicator. And for weak acid, strong base, because the salt is slightly basic, that means our solution will also be slightly basic once the weak acid and strong base have been completely neutralized. And that means we use phenolphthalein to check the endpoint, so to get our equivalence point. So know the indicators and why we use different indicators, know the different types of pHs and why these different pHs exist, and be able to sort of remember these type of graphs, how the graphs look for each of those type of titrations. In the next video, we're going to cover some of the problems, solve some of the problems for titrations. I hope that was useful.
Thank you for watching.